What's going on, everybody? It's Mr. Gus, and I'm back in the physics conference room where I'm talking about electric potential or voltage today. But first, let's talk about gravity because there's a lot of similarities between gravitational potential and between electric potential. So we'll start with something we know, that's gravity. So I've got an object. I've got a lead rock, this heavy object, and this very small pebble, and I drop them both towards the earth at the same time. When I do that, I ask myself which one's going to hit the ground going faster. It's a very basic physics question, but which one hits the ground going faster? Let's solve it in terms of energy. If it's energy, I would say that they both have UG above the ground, and at the ground they both have K. Well, if I start making my equation for my conservation of energy, what I quickly see is that both objects have the exact same initial algebra, right? This GH thing equals 1/2 v squared. Do either of these objects have different G's? No. Do either of these objects have different heights above the earth? No. So what happens is, so which of these objects hits the ground first? Well, they both hit the ground with the exact same speed. V of the rock is equal to V of the pebble at the ground. Why? Well, it's because that the mass doesn't really affect how the acceleration or the rate of acceleration this thing falls to the ground. What really affects this thing, and people often forget this, is the earth. The only thing that is attracting these objects to the ground is the ground itself, is the earth. So we give this type of attraction between the ground itself because we don't always know the masses of objects, so sometimes it's just easier to talk about the strength of the pull the Earth has on all objects, regardless of mass. And so we call this GH thing, we call this our gravitational potential. And gravitational potential literally means is the potential for gravity to act on something. And it's measured in gravitational potential, or let's just call it GP, for example. That is equal to our amount of potential energy per mass, meaning this gravitational potential is a relationship for the amount of gravitational potential energy that is possible or potential per kilogram of mass. So, which of these objects will have a larger gravitational potential energy? The one with the larger mass has more gravitational potential energy, but both are within this field of the Earth. Both have the same gravitational potential. It's just that their mass affects the amount of energy that they have, the amount of work they're able to do. Very similar to this, we have what is called electric potential energy or voltage. We can call it electric potential energy. Electric potential. Or we call it voltage. And voltage has an equation. Voltage is equal to the amount of electric potential energy divided by the amount of charge. This is our kind of analogy, if you will, right? If gravity is the amount of potential energy per mass, well then voltage or electric potential is the amount of electric potential energy per charge. So imagine this positive charge. This is our Earth. This is the object that is either attracting or repelling objects of charge. Because we don't talk about charges attracting mass. We're talking about charges attracting or repelling other objects that are charged. So, if I think about a positive test charge or a positive charge located right here, it is going to have a different potential, meaning there's going to be a different amount of gravitational potential energy between those two objects than, say, if I move that charge way out here. Those two things have different amounts of electric potential energy. But it's unreasonable for us to assume we always will know the amount of charge something has. So it's more likely, it's easier for us to discuss this charge, this Earth charge itself, with a measurement known as voltage or electric potential. We can calculate the electric potential in a different way besides this. Instead, if we do the algebra for this, we plug in our equation for UE and divide it by the test charge, we end up with this equation. Voltage is KQ, and we'll call this guy big Q, we'll call this guy little q, over R. So what is voltage dependent on? Voltage, or electric potential, the ability to have electric potential energy, is equal to the charge itself, the Earth, the big thing attracting or repelling something, divided by the distance you are away. This is incredibly similar to gravitation. Why? Because gravitation is dependent on what? Gravitation is dependent on the Earth, baby G, and how far away you are from that Earth. This is the exact same concept as electric potential energy. It tells us if the Earth changes, baby G changes. If you change the location of mass, well then this also changes, just like we have over here with voltage or electric potential. If you change the location of the mass, you change its potential to have potential energy. And if you change the size of this charge, well, you change the ability for that thing to have electric potential energy. Now, that being said, a very useful tool is not exactly calculating the specific voltage at a location, but calculating the change in potential from one location to the next, indicating the amount of possible energy between 2 points. And we call this a potential difference or difference in potential. How do we calculate that? We would look at a change in electric potential energy per charge. So for example, if I was going to move this object, this positive charge, from R1 over here to R4, I would be able to calculate what is the potential energy here, what is the potential energy over here. I would subtract final minus initial and divide it by whatever baby Q is right there. And this would tell me how much potential difference there is between two locations, tell me how much energy I would have if a certain amount of charge was there to move. Batteries are measured in voltage. We don't really know how many charges are in batteries, so instead we call them 1.5 volt batteries, meaning whatever you pop that thing into, however many charges are in that battery, we know what is going to happen. We know how much work can be done given the charge in that battery. This is why you see car batteries are only 12 volts, but they're pretty dangerous because of the amount of charge in them. There are other 12 volt batteries. You go camping with some 12 volt batteries. There's other batteries that are also 12 volts or 9 volts or 1.5 volts, right? It's not so much the voltage that matters, but the charge that is in that battery that the voltage can push, okay? We're trying to come up with this idea, this concept of voltage. I hope this helps, but this is what voltage or electric potential is. And remember, it's not so much voltage that matters as it is this change in voltage that we're really tracking, how much the change energy per charge that an object has. That object is our Earth charge or the stationary kind of charge we have here. Okay? If you got questions, drop in the comments, send me an email, or ask me in class. All right? Till next time. See ya.